Welcome to Sleepy Space Science, where James Webb's Little Red Dots suggest black holes before galaxies. Tiny red points appear in ancient infrared darkness, hiding engines that may outgrow their galaxies. Webb sees what older views missed because stretched early light now arrives as infrared whispers. The dots gather during a brief window, rising early before fading from cosmic abundance later. Their timing turns scattered specks into a phase not merely random crimson decoration across space. A spectrum opens each dot like a fingerprint revealing motion gas dust and hidden accretion. Broad lines hint at violent nearby orbits, yet familiar black hole patterns remain strangely incomplete still. Dense cocoons may trap young black holes, reddening their light through turbulent surrounding gas shells. Around hidden engines, fuel becomes both nourishment and veil, making growth look deceptively quiet outside. The growth problem begins when heavy candidates appear before ordinary stellar remnants seem sufficient enough. Some dots may be stars and dust instead, blending several early processes together inside them. Capers-LD-Z9 sharpens the case, showing confirmed broadline accretion in an extraordinarily early red dot system. One extreme example does not define all dots, but it raises the pressure sharply now. If accretion lights the dots, their galaxies may be lighter than first imagined by astronomers. Seed theories divide the darkness between small remnants, heavy collapse, and crowded early stellar nurseries. Missing X-rays deepen the puzzle because silence can mean burial, or another hidden source entirely. In early space, absence becomes evidence, drawing outlines around what light cannot fully escape there. Future tests must compare many wavelengths, searching for variability, hot dust, and ionized clues together. Each added wavelength turns the dots slightly, like a locked object, revealing hidden edges slowly. The phrase "before galaxies" means early black hole growth inside systems not yet mature or settled. Galaxies and black holes may have grown together, tangled in gas before clear structure emerged. The red dots become doorways, making the young universe stranger readable and still unfinished again. Please like, subscribe, and thank you for listening as the first red dots begin appearing. At first, the little red dots look almost too small to carry a cosmic mystery. They sit in James Webb's deep images as faint red points, quiet and compact, without the spiral arms or glowing halos that make a galaxy feel familiar. A tired eye could pass over them as background specks, distant objects among thousands softened by ancient light. But the strange part is not their size in the image. The strange part is what their light may be hiding. Some of these objects appear in a young universe, during an era when galaxies are still assembling. Stars are enriching space, and the first large structures have not yet settled into familiar shapes. They are red partly because their light has crossed an expanding universe stretched toward infrared wavelengths before reaching Webb. They are little because they are distant and compact. But when astronomers begin to separate their light, the simple picture becomes less comfortable. The dots may not be ordinary baby galaxies glowing only with stars. Some may contain young black holes growing faster or earlier than older expectations made easy to imagine. That is the problem. A black hole cannot be seen directly because light cannot escape from within its event horizon. Yet a feeding black hole can make itself known through the material falling toward it. Gas heats, accelerates, collides, and shines before it crosses the boundary of no return. Around familiar active galaxies, that feeding can produce bright signatures across many wavelengths. But the little red dots do not always behave like those familiar systems. They seem compact. They seem red. Some show spectral signs that can be read as fast-moving gas. Yet many do not blaze with obvious X-ray or radio power that would make the black hole answer simple. The image is quiet. The implication is not. To understand why these dots matter, it helps to imagine Webb not as a camera looking outward, but as a clock reading backward. The farther a galaxy is, the longer its light has travelled. A point of light from the early universe is not only a place in space, it is a record from younger time. When Webb sees these red, compact objects, it is seeing them as they were when the universe was only a small fraction of its present age. The stars inside them, if stars dominate the light, are part of an early generation of galactic building. The gas inside them, if gas shapes the light, belongs to a universe still thick with raw material. And any black holes inside them, if black holes are truly present, are being observed during a stage that could reveal how enormous cosmic engines first began to grow. That possibility turns a red speck into a doorway. The familiar story is that galaxies form gather stars, build structure, and over time feed the black holes at their centers. In the nearby universe, supermassive black holes are often found in the hearts of massive galaxies, as if the galaxy and its dark central engine have grown together through gravity gas mergers and time. This picture is not wrong, but Webb is making it less simple. If some little red dots are powered by accreting black holes, then black hole growth may already be important while the surrounding galaxies are still young and compact. The old sequence begins to blur. This does not mean black holes formed before every galaxy, and it does not mean the mystery is solved. The safer idea is more precise. Webb may be revealing a phase in which young galaxies and young massive black holes are growing together so tightly that their light is difficult to separate. That distinction matters. A dramatic claim can be easy to remember, but a careful claim is often stranger. A little red dot may look like a simple early galaxy, until its spectrum suggests motion too fast for ordinary starlight alone. It may look too massive until part of its brightness is reassigned to an accreting black hole or dense glowing gas. It may look like a missing piece of black hole history, while still remaining mixed with stars' dust and uncertainty. In this way, the dots behave less like answers and more like pressure points. They press on the boundary between galaxy formation and black hole formation. They press on the question of how fast matter can fall into a young black hole. They press on the problem of how early the universe could build compact engines powerful enough to reshape their surroundings. The clue is small, but it is not empty. The red color also carries a double meaning. Some of it comes from distance because cosmic expansion stretches early light before it reaches a telescope. Some may come from dust or gas inside the object itself, absorbing shorter wavelengths and letting redder light escape. Some may come from older-looking stellar populations packed into compact regions, and some may come from the reprocessed glow around a buried black hole where energetic radiation is softened by surrounding material. Each possibility changes the story. If the light is mostly stars, the question becomes how compact stellar systems formed so early. If the light is mostly dust-obscured star formation, the question becomes how quickly the first galaxies became chemically rich and hidden. If the light is shaped by accretion, the question becomes how black holes began feeding before their host galaxies became familiar. The same red dot can hold several possible histories at once. Section 1 begins with that uncertainty because the mystery depends on it. Webb has not simply found a new kind of pretty object. It has found a class of faint red signals that make the early universe harder to sort into clean categories. Some may be young galaxies, some may be black holes wrapped in gas, some may be both. The first lesson is not certainty but compression, enormous questions folded into tiny points of light. What looks like a dot may contain stars, dust gas gravity, and a hidden engine still learning how to grow. And before the black hole question can be answered, one deeper question has to come first. Why did Webb see these objects so clearly when older telescopes could only leave much of this red early population in the dark? Webb sees the little red dots because the early universe does not send its oldest light to us in the form it first had. A young galaxy may begin by shining in ultraviolet and visible wavelengths bright with hot stars and heated gas, but the journey across expanding space changes that light before it arrives. As space stretches, the light stretches with it. What was once bluer becomes redder. What was once visible can slide into the infrared beyond the main reach of older optical eyes. This is why a telescope built to read infrared light becomes a kind of time instrument. Webb does not merely look farther by collecting more light. It looks differently in the range where the ancient universe has placed its faintest messages. The little red dots belong to that hidden range. They are not red in the simple way a nearby ember is red, or a cool star is red, or a dusty sunset is red. Their redness is partly a record of distance expansion and time. The image is small, but the journey is enormous. Before Webb, the Hubble Space Telescope had already opened deep windows into the young universe. Hubble showed fields filled with galaxies at many distances, some so remote that their light had travelled for most of cosmic history. But Hubble was strongest in optical and near-infrared light compared with Webb's deeper infrared power, and there were limits to what it could separate, measure, and confirm at the highest redshifts. Many early objects were present as hints, candidates, or faint smudges. Their light was often too weak, too stretched, or too blended with uncertainty to reveal a fuller shape. Webb changed that by combining a large mirror-cold instruments and infrared sensitivity designed for the earliest accessible galaxies. It could gather light that older telescopes struggled to read. It could see compact red sources in surveys where the first interpretation was not always obvious. It could take spectra and ask not only where the dot was, but what kind of physical system produced the light. That shift matters because a picture alone can make the universe look simpler than it is. A point of light can seem like a single object with a single meaning. But in astronomy, a point is often an unresolved structure. It may contain stars packed close together. It may contain dust that changes the colour. It may contain gas moving under gravity. It may contain a black hole whose presence is hidden in the behaviour of matter around it. Webb's advantage is not that it turns every dot into a detailed portrait. Many little red dots remain too compact for that. Its advantage is that it can read more of the light, and light carries layered information. The wavelength tells a story of distance. The brightness tells a story of energy. The spectrum tells a story of atoms' motion and conditions. A tiny red point becomes less like a speck and more like a sealed envelope. Webb is beginning to open it. The key is the early universe itself. When light has travelled for more than 13 billion years, it does not arrive as a simple photograph from far away. It arrives as a change signal from a change cosmos. The universe has expanded during the journey, and the expansion leaves an imprint on the light. Astronomers call this redshift, but the word can sound too neat for what it means. It means the object is not merely far across space, it is far back in time. A high redshift object is a message from an earlier cosmic environment before the universe had built most of the mature structures seen nearby. In that environment, galaxies may be smaller, denser, more gas-rich, and more chaotic. Stars may form in intense bursts. Black holes, if present, may be buried inside the same dense material that feeds them. The surroundings are not clean. That is why Webb's infrared vision is so important. It does not remove the uncertainty, but it brings the uncertainty into focus. The little red dots are especially provocative because they gather several difficult clues into one small appearance. They are compact enough that their true shapes can be hard to resolve. They're red enough that ordinary explanations must be tested carefully. They are numerous enough in some early surveys to suggest a broader population rather than a single odd accident. And some show spectral features that make accreting black holes a serious possibility. Without Webb, many of those clues might remain below the threshold of confidence hidden in noise or unobserved wavelengths. With Webb, the dots become measurable. Not fully explained, but measurable. That difference is where modern astronomy often begins. It begins not with final answers, but with better questions produced by better instruments. There is also a quiet reversal here. In everyday seeing, a red dot might feel small, weak, or distant from importance. In Webb's universe, redness can be the mark of ancientness. Compactness can be the mark of distance. Faintness can be the shadow of enormous time. A little red dot is little only because the universe has placed it near the edge of observable history. Its physical system may be large compared with human scales filled with stars, gas dust, and perhaps a central engine. The mind sees a dot. The instrument reads an epoch. That is the first transformation Webb provides. It changes faint marks into historical evidence. It turns colour into time. It turns a small red source into a question about how early structure formed. But seeing these objects is only the beginning. Once Webb reveals them, astronomers must ask whether they are scattered randomly across early time or whether they appear most strongly during a particular cosmic interval. And that is where the dots become even stranger, because their abundance may rise and fall like a brief phase in the young universe, rather than a simple population spread evenly through history. The little red dots become stranger when they stop looking like isolated discoveries and begin to look like a timed appearance. A single object can be treated as an exception, a rare accident found because a telescope happened to look. But a population is different. A population has a pattern, and patterns ask for causes. In Webb's early surveys, these compact red sources seem to emerge in large numbers around a time when the universe is only hundreds of millions of years old, then decline as cosmic history moves toward more mature galaxies. The census will change as samples grow, selection methods improve, and astronomers argue over what belongs in the category. But the broad idea is already powerful. The little red dots do not feel scattered evenly through all time. They seem tied to a particular early interval, as if the young universe briefly made conditions favorable for objects that later became harder to find or recognize. Time is not only background in this story. Time is part of the evidence. In a familiar picture of galaxy growth, early systems gather gas-formed stars, merge with neighbours, and gradually build larger structures. Black holes may grow inside them, but the process is usually imagined as something that unfolds through long supply lines of matter and repeated episodes of feeding. There is nothing strange about young galaxies existing early. That is expected. There is nothing strange about black holes existing early either, because the first massive stars can die and leave remnants. The difficulty begins when compact early objects seem bright, numerous, and spectrally complex enough to suggest that something more intense may be happening inside them. If the dots mark accreting black holes, then the early universe was not merely planting small seeds and waiting patiently. It may have been feeding some seeds in dense, hidden environments before the host galaxies had time to become large and relaxed. The first answer is simple. The second answer is stranger. The timing also helps separate little red dots from ordinary distant galaxies. A normal early galaxy should not vanish as a class just because the universe grows older. It may evolve, brighten, fade, merge, or change color, but if the same physical conditions remain common, similar objects should continue to appear. A strong rise and fall suggests a phase. A phase is not simply an object, it is a temporary state. A caterpillar and a butterfly are not unrelated creatures, but they do not look the same because one is a stage on the way to another. In the same quiet way, a little red dot may be a stage in the early life of a compact galaxy, and its central engine not a permanent category. It may be a moment when gas is dense dust, or ionized material is wrapped close around the source, stars are forming rapidly, and any black hole inside is still hidden inside the material that feeds it. The dot is not just a thing, it may be a condition. This idea gives the red color a deeper role. If the objects are common during a narrow young era, then their redness may reflect more than distance. Cosmic expansion stretches their ancient light, but local conditions inside the objects may also redden and reshape the signal. Thick gas can absorb and scatter radiation. Dust can dim bluer light. Dense stellar populations can add their own glow. Accretion can produce energetic light that is reprocessed before escaping. The result is a compact source that looks simple in an image and complicated in a spectrum. The same dot carries both universal time and local physics. One part of the redness says the light has travelled across an expanding cosmos. Another part may say the source itself is wrapped, crowded, and hard to see through. That double meaning is why the timing matters so much. The listener can picture this as a foggy harbour at dawn. Only small lamps are visible through the mist, and each lamp looks like a point. The lamps do not tell the whole shape of the ships, the docks, or the water around them. But the fact that many lamps appear only during the foggy hour says something about the environment. When the fog lifts, the same harbour may still exist, but the appearance changes. The little red dots may be like those lamps' compact visible signs of larger systems hidden by the conditions of their time. The comparison is imperfect, but it helps hold the scale. The early universe is a vast expanding medium filled with gas, radiation, gravity, and the first generations of structure. Still, the principle is useful. What is visible depends on the environment through which the light escapes. A timed appearance can reveal not only objects but conditions. This does not prove that all little red dots are black holes. It does not even prove that one explanation dominates the entire population. Some may be compact star-forming galaxies, some may be dust-obscured systems, some may contain active black holes buried inside dense gas. Some may combine these ingredients in ways that make clean labels difficult. But the early window forces the question to sharpen. Why would so many compact red sources appear when the universe is young and then become rarer as it matures? What changes? Does the supply of dense gas thin out? Do black holes clear the material hiding them? Do the host galaxies grow larger, making the same central engines less visually compact? The evidence does not give a final answer. It gives a direction. Section 3 is the moment when the mystery becomes historical. The little red dots are no longer just faint points found by a powerful telescope. They become markers on a cosmic timeline, signs of a possible phase when early galaxies' dense gas and growing black holes may have been entangled in a way that later became less common. Their timing suggests that the old model of gradual orderly growth may be incomplete, not because it is useless, but because it may miss the hidden intensity of the first billion years. And once the clock is recognized, the next question becomes sharper. What did scientists expect early galaxies and their black holes to look like before Webb revealed this red population? Before Webb turned the little red dots into a population, the early universe was imagined through a slower and cleaner sequence. Gas gathered first. Small dark matter halos pulled matter inward. The first stars lit up. Young galaxies formed in pieces collided, merged, and gradually became larger systems. Black holes could appear inside this story, but they were placed under the pressure of time. A small black hole left behind by a massive first star would need to feed with remarkable efficiency to become enormous quickly. A heavier seed might grow faster, but heavier seeds require special birth conditions. In either case, the old picture left room for early black holes, yet it did not make them easy. They were expected to be rare, difficult to see, and dependent on environments that could keep feeding them without tearing the surrounding galaxy apart. The universe could build them, but the schedule was tight. That was the quiet assumption. Early galaxies, in this view, were not supposed to look too mature too soon. They could be bright from young stars because the first billion years contains intense star formation. They could be irregular, clumpy, and gas-rich because they had not yet settled into the grand spirals and smooth ellipticals familiar nearby. They could host black holes, but the black holes were expected to be small or uncommon unless something special had happened. This was not a foolish model. It followed from gravity stellar death gas cooling and the limited amount of time available after the Big Bang. A few 100 million years is enormous compared with a human life, but in cosmic construction it is as narrow morning. To build a massive galaxy, enrich it, with heavier elements, grow a central engine and hide that engine inside dust or gas requires many processes to move together. The old model did not forbid surprises. It simply made some surprises expensive. Then the red compact sources began to apply pressure. If a little red dot were only a small young galaxy filled with new stars, the old model could absorb it more easily. The early universe should contain small galaxies. It should contain hot young stars. It should contain objects too faint or compact for older telescopes to classify well. But some little red dots did not sit comfortably in that simple category. Their colours, compact sizes, and spectral features suggested that starlight alone might not be the whole explanation. In some cases, the light appeared to carry broad emission lines, the kind of widened spectral marks that can happen when gas moves extremely fast. Fast gas is a clue, because gas moving under strong gravity near a black hole can reach speeds far beyond ordinary galactic motion. The measurement does not solve the mystery, it sharpens it. A spectrum is often where astronomy stops being a picture and becomes a physical investigation. The image says there is a red point. The spectrum asks what atoms are present, how the light has been stretched, and how the emitting gas is moving. If an emission line is narrow, the gas may be moving at speeds associated with broader galactic regions. If the line is broad, the gas may be orbiting close to a powerful compact source. This is why broad lines matter in the little red dot story. They can point toward active galactic nuclei systems where a black hole is feeding and the surrounding gas is heated and accelerated. But broad lines must be interpreted carefully. The early universe is not a laboratory with one clean variable. Dense gas dust star formation and black hole accretion can overlap in the same unresolved object. A fingerprint can be smudged. Still, the fingerprint is there. This is where the old expectation begins to bend. The early objects were supposed to be hard to classify, but not necessarily so full of hints that black holes might already be common in compact red systems. If many little red dots contain accreting black holes, then the first billion years was not merely an era of small galaxies waiting to become larger. It was also an era of hidden engines feeding inside dense young structures. The galaxies and black holes may not have taken turns. They may have grown together, each shaping the other, while both were still difficult to separate. That possibility changes the question from when did galaxies make black holes to how early did black holes begin changing galaxies. It is a subtle shift, but it moves the story. The human mind wants a sequence first, the house, then the furnace inside it. But the early universe may have built the furnace while the walls were still rising. The comparison is imperfect because galaxies are not houses, and black holes are not machines placed neatly inside them. Yet the image helps. If the central engine is already active while the host system is still compact and gas-rich, then the light escaping from the structure becomes tangled. Some photons come from stars, some come from gas, some may come from the heated region around a black hole. Some are absorbed and re-emitted before leaving. By the time that light crosses billions of years and reaches Webb, the object has become a tiny red summary of hidden processes. The old model expected complexity. The dots suggest a different kind of complexity compression. This does not mean the earlier framework collapses. A strong scientific model is not destroyed every time a new object appears. It is adjusted, tested, and sometimes expanded. The little red dots do not announce that galaxy formation was wrong. They ask whether a missing phase has been undercounted, a brief early stage when small galaxies, dense gas cocoons, and growing black holes were common enough to leave a recognizable red signature. The old model gave astronomers the right reasons to be cautious. Webb gives them better reasons to be curious. And curiosity now has a sharper tool than color alone to move beyond appearance. And the next step is to read the light itself as a layered record of atoms' velocity, dust, and gravity, because the answer to the black hole question is not hidden in the dot's shape. It is hidden in the way the dot's light has been stretched, broadened, and filtered before it arrives. The next clue is not what the little red dots show at first glance, but what they refuse to show in the expected way. If a compact red object contains an actively feeding black hole, the familiar model gives astronomers a pattern to look for. Material spirals inward. The gas becomes hot. Radiation pours out. High-energy light may appear in X-rays. Jets or radio structures may appear if magnetic fields and outflows become organized. Broad emission lines can mark gas moving rapidly near the central engine. In nearby active galaxies, these pieces often form a recognizable family of evidence enough that the category feels familiar. The little red dots disturb that familiarity. Some carry spectral hints that resemble black hole feeding, especially broad lines that suggest fast-moving gas. Yet many do not shine with the X-ray or radio strength that a simple, active black hole picture would make easy to expect. The clue is present, but the usual surroundings are missing. That mismatch is where the story becomes more difficult. A black hole itself remains dark, but a feeding black hole can be loud. The accretion disk around it can heat to extreme temperatures. Gas close to the center can orbit so quickly that the light from its atoms is smeared across a wider range of wavelengths. This broadening is not merely a visual blur, it is a record of motion. When gas moves toward and away from the observer at high speeds, the emitted light shifts slightly, spreading a once narrow line into a wider feature. In many active galactic nuclei, broad lines are one of the classic signs that gas is moving under the influence of a massive compact object. For little red dots, this is one reason the black hole interpretation survives. The spectra do not always look like pure starlight. They can look as though something dense and energetic is hidden inside. But the rest of the expected signature is often muted. The meaning is harder. If the central engine is real, then something may be changing the way its light escapes. One possibility is that the black hole is buried in gas. In the young universe, compact galaxies may contain raw material packed into small regions. Gas can feed stars, It can feed a black hole. It can also hide the very process it supplies. A buried black hole may produce energetic radiation near its center, but that radiation does not necessarily travel freely into space. It may strike surrounding gas, scatter from electrons, be absorbed, or be re-emitted at longer wavelengths. By the time the light escapes, the object no longer resembles a clean exposed active nucleus. It resembles a compact red source with strange spectral lines and a missing high-energy voice. The black hole may be there, but wrapped in the evidence that makes it hard to prove. This is the hidden mechanism that begins to connect the contradictions. Imagine a lantern placed inside thick, moving fog. The lantern is real, but the light that reaches the outside is softened, reddened, and blurred. If the fog is dense enough, a person far away might see only a small, warm glow and not the lamp itself. If the fog is moving, the glow may change shape. If the fog has openings, some sharper light may leak through. A young black hole inside a little red dot may not announce itself like a clean beacon. It may be seen through the gas that surrounds it, and that gas may be both fuel and veil. The surrounding gas is not decoration. It may be the main reason the objects look strange. A dense cocoon can also change how broad lines are understood. In a simple, active black hole, picture broad lines may mean gas is moving quickly because it is close to the black hole. But recent models suggest that in some little red dots, part of the broadening may come from electron scattering inside dense ionized gas. In that case, the line does not only measure orbital motion near the central engine, it also records the conditions of the material wrapped around it. The black holes may still be present, and they may still be young and rapidly growing, but some measurements that first seem to imply unusually massive black holes could be affected by the surrounding medium. The object does not become ordinary, it becomes more layered. The apparent contradiction begins to look like a physical system. This also explains why the old model is not simply wrong, but incomplete. Active black holes have had more time to clear channels and become visible in familiar ways. Early black holes, if the little red dots contain them, may be caught before that clearing is complete. They may be feeding inside crowded nurseries where gas has not yet been pushed away, and where the host galaxy remains compact and unsettled. The central engine, the gas supply, and the forming galaxy overlap in one unresolved source. That overlap makes classification difficult. Starlight can mimic part of the signal. Dust can change the color. Accretion can add hidden energy. Scattering can widen lines. Absorption can silence X-rays. Each clue points somewhere, but no clue stands alone. The micro payoff is that the little red dots do not need to behave like mature active galaxies in order to contain black holes. They may represent an earlier buried stage when the engine is present, but its light is still being processed by the material around it. The dots do not break the rules. They show that the same rules can produce unfamiliar appearances under unfamiliar conditions. If dense gas surrounds a growing black hole, then redness, broad lines, weak X-rays, and compact size can become parts of one story instead of separate puzzles. Still, this explanation is not a final verdict. It must compete with star-heavy galaxies, dusty star formation, and other early universe possibilities. The next question is therefore not whether one dot can be forced into one category, but whether the broader population follows the same pattern. If many little red dots share these hidden engine signatures, then Webb may be revealing a common early phase of black hole growth. If they do not, the red dots may be a mixed family, whose members only look alike from far away. A dense cocoon is a strange answer because it makes the black hole both more hidden and more believable. If the little red dots contain young accreting black holes, the surrounding gas cannot be treated as empty scenery. It may be the central part of the mystery. In a mature active galaxy, the black hole can sit inside a system where radiation has opened channels, where dust has been rearranged, and where the central engine may be visible through familiar signatures. But in the early universe, a compact galaxy may still be crowded with the same material that is building its stars and feeding its center. Gas falls inward, radiation pushes outward, gravity compresses, electrons scatter light, atoms absorb and emit. The result may be a young black hole wrapped inside its own supply. The engine is not absent, it is muffled. That is why the cocoon idea matters. It does not ask the red dots to behave like nearby active galaxies. It asks what an active black hole would look like before it has fully escaped its birth environment. The word cocoon can sound soft, but the physics behind it is not gentle. The gas around a growing black hole can be ionized, meaning its atoms have been stripped of electrons by intense radiation. Free electrons then become a moving screen. Light passing through them can scatter change direction and lose the clean simplicity it might have had near the source. Emission lines that might otherwise be read as a direct measure of gas orbiting close to the black hole can become broadened by the surrounding medium. X-rays that should escape from the hot inner region may be absorbed or reprocessed. Radio emission may remain weak or difficult to detect. The black hole still feeds, but the evidence arrives wearing the signature of the envelope around it. The clue is not only the engine, the clue is the wrapping. This changes how the little red dots can be interpreted. If broad lines are seen, astronomers might first estimate a black hole mass by assuming that the line width mostly reflects gas moving under the black hole's gravity. That assumption can be useful in many contexts, but if dense ionized gas also broadens the line through scattering, then the first estimate may be misleading. The black hole might be less massive than it first appears while still accreting rapidly enough to matter. This is important because some early interpretations made the dots look almost too massive, as if they strained the timeline of cosmic growth. A cocoon model can soften that tension. The objects remain unusual, but they become less impossible. They may not be overgrown monsters sitting where they should not exist. They may be younger, lower-mass black holes feeding hard behind dense gas, with their light distorted by the material that helps them grow. Picture a small furnace inside a sealed room filled with steam. From outside, the observer cannot see the furnace directly. The walls glow faintly. The steam carries heat. Shadows blur. A sound that should be sharp becomes softened. The observer knows there may be a powerful source inside, not because the source is visible, but because the room behaves as if energy is trapped and redistributed within it. A little red dot may work in a cosmic version of that logic. Webb sees the escaping glow after it has been filtered through gas-dust motion and immense distance. What reaches the telescope is not a simple portrait of the black hole. It is the aftermath of radiation trying to leave a crowded place. The visible dot is the outer sentence of an inner story. The cocoon hypothesis also explains why the little red dots can feel like a phase rather than a permanent category. A cocoon does not have to last forever. As a black hole feeds, it can heat and disturb nearby gas. As stars form, they can inject radiation and winds. As the compact galaxy evolves, mergers and internal motion can rearrange the material. Eventually, some gas may be consumed, expelled, or spread into a larger structure. The buried engine may become easier to see, or it may fade if the fuel supply changes. This would make the little red dot stage temporary, a moment when the black hole is active, the galaxy is compact, and the surrounding material is dense enough to hide the central source, while still letting reprocessed light escape. The red dot is not merely an object. It is a condition caught in time. Still, the cocoon idea must not be treated as a final label stamped onto every red point. A dense gas envelope can explain several clues, but other pathways remain possible. Compact star formation can create bright light. Dust can redden a galaxy. Older stellar populations can affect colors. Tidal disruption events or other temporary flares may mimic parts of the signal in some cases. The early universe is crowded with overlapping processes, and Webb often sees them blended together into a source too small to separate visually. That is why the strongest interpretation is not that every little red dot is the same kind of buried black hole. The stronger, safer idea is that dense cocoons may reveal one important channel by which young black holes grow before they become obvious. The evidence becomes a map of possibility, not a verdict. The micro payoff is that the contradictions begin to fit together. Red colors, compact shapes, broad lines, and weak high-energy signals do not have to pull in separate directions. They can describe a young active nucleus wrapped in dense material seen during the stage when feeding and hiding happen at the same time. If this is correct for a substantial part of the population, then Webb has not merely found black holes early. It has found them during a hidden childhood, before the host galaxies and the engines inside them have separated into the cleaner forms astronomers know nearby. But this answer opens a larger problem. A cocoon can hide a growing black hole, and it can make the black hole seem less massive than first feared. It cannot by itself explain how the seed began, how the fuel arrived, or how the growth stayed fast enough in a universe so young. The growth problem begins with a clock that cannot be negotiated. A black hole may feed fiercely, but it still needs time fuel, and a way to keep radiation from pushing that fuel away. In the nearby universe, supermassive black holes can be millions or billions of times the mass of the Sun sitting in galactic centers after long histories of mergers and repeated feeding. In the early universe, the clock is younger. If a little red dot contains an actively growing black hole only a few 100 million years after the Big Bang, then the black hole has not had the luxury of slow construction across billions of years. It must have begun from a seed and then grown quickly, or it must have begun from a seed already heavier than stellar death can easily provide. That is the pressure point. The question is not whether black holes can grow. They can. The question is whether they can grow enough soon enough under the conditions Webb is beginning to reveal. The simplest seed is the remnant of a massive early star. A star far more massive than the Sun can end its life by collapsing into a black hole, leaving behind a compact object with a head start. In principle, such a seed can feed on nearby gas and become larger. Over enough time, accretion and mergers can build something immense. But the first billion years is not enough time for every comfortable pathway. If the seed begins small, it may need long periods of efficient feeding. Feeding has a limit because falling gas releases radiation, and that radiation pushes outward. At a certain point, the outward pressure can balance the inward pull on the gas, slowing the supply. Astronomers call this balance the Eddington limit, but the name matters less than the image. A black hole can be hungry, yet its own light can push dinner away. One way around the problem is to begin with a heavier seed. Instead of forming only from the collapse of a stellar remnant, a black hole might begin when a large cloud of gas collapses more directly, producing a much more massive starting point. Such direct collapse ideas are attractive because they shorten the growth ladder. A seed that begins heavier does not need as many doublings to reach a large mass early. But heavy seeds are not free. They require special conditions. Gas must collapse without fragmenting too efficiently into ordinary stars. Cooling, radiation, chemistry, turbulence, and the surrounding environment all matter. The early universe may provide some conditions, especially before heavy elements become widespread, but the pathway is still debated. A heavy seed solves one time problem by creating another birth problem. The answer becomes possible, not simple. Another way around the clock is faster feeding. A black hole may sometimes grow above the ordinary steady rate if gas arrives in a thick flow that traps radiation or funnels material inward despite outward pressure. This is often discussed as super Eddington accretion. It does not mean the black hole ignores physics. It means the geometry, density, and behavior of the inflowing material may allow growth to exceed the simple limit for a time. In the Little Red Dot story, dense cocoons make this possibility especially interesting. If a black hole is wrapped in gas, the same environment that hides its light may also help deliver fuel. The veil may be part of the engine. But fast feeding must be sustained enough to matter. The human-scale picture is a fire in a sealed furnace. If fuel reaches the fire slowly, the flame grows slowly. If fuel pours in too quickly, heat and pressure can choke the flow or force smoke outward. But if the chamber is shaped in a certain way, pressure can be trapped or vented while fuel continues to enter. A young black hole is not a furnace, yet the comparison helps make the conflict visible. Gravity pulls matter inward. Radiation pushes outward. Gas geometry decides how much material actually reaches the center. In a compact early galaxy, the same process may be buried and uneven. Growth is not just hunger. Growth is a negotiation between gravity and escape. This is why little red dots matter so much. They may reveal black holes not after they have already become grand central engines, but during the struggle to become them. If the dots contain low-mass young black holes in dense gas, then they may show the missing bridge between seed black holes and the enormous quasars observed later in cosmic history. If some dots contain heavier seeds, they may point to rare early collapse conditions. If some contain smaller seeds feeding at extreme rates, they may show that growth can be temporarily more efficient than simple models assumed. Each interpretation changes the origin story. The objects are small in the image, but they sit at the center of a large question. How does the universe turn darkness into engines? The micro payoff is that the growth problem is not one problem, but three linked problems. There is the seed problem, how large the first black hole was when it began. There is the fuel problem, how much gas could reach it without being blown away. And there is the visibility problem, how the surrounding material changed, the light astronomers now observe. Little red dots touch all three. Their spectra may hint at accretion. Their colours may hint at envelopes of gas or dust. Their early timing makes slow growth harder to rely on. They do not prove one pathway, but they make the missing early stages harder to ignore. The answer is partial. That is why it matters. Still, the growth problem also warns against overreading the dots. A broad line may not give a simple black hole mass if dense gas scatters the light. A bright red source may not be massive in stars if an active nucleus contributes much of the glow. So the next layer is not just how black holes grow, but whether the easy explanation for the dots survives at all. Perhaps the black hole interpretation is right for many of them. Perhaps stars and dust can explain more than expected. Perhaps the population is mixed. The next question must test the simplest answers against the evidence. The easy explanation fails because the little red dots are too good at imitating several things. If they were only young galaxies filled with stars, their redness could be explained by distance dust or old-looking stellar light packed into a small early system. If they were only black holes, their broad lines and compact brightness would seem easier to understand. If they were dusty starbursts, their red colours might come from young stars hidden behind newly made grains. But each simple answer leaves something behind. Stars can explain much of the light in some objects, but not always the broadest signs of fast gas. Black holes can explain accretion-like spectra, but not always the weak X-ray and radio behavior. Dust can redden a galaxy, but dust alone does not automatically create every observed feature. The dots refuse to become one clean category. That refusal is the clue. The first competing explanation is that many little red dots are compact early galaxies whose light is dominated by stars. In the young universe, galaxies are expected to be smaller, denser, and less settled than nearby galaxies. Their stars can form in intense bursts, and their light can be packed into regions that Webb sees as nearly point-like. If enough stars are present, or if the stellar population has unusual properties, the object can appear bright and red. This answer has an attractive simplicity, because it does not require a hidden central engine in every case. It keeps the mystery within galaxy formation. But it also creates pressure. If the red light is mostly stellar, some objects may appear surprisingly massive for their age. Astronomers then have to ask how so many stars formed so early, how they became so compact, and why the population seems to fade with time. The second explanation is dust-obscured star formation. Dust is not dirt in the ordinary sense. It is tiny solid material formed from heavier elements, able to absorb blue and ultraviolet light, and re-emit energy at longer wavelengths. A young galaxy rich in dust can look redder than it would without that veil. This can make an object seem older or stranger than it is, but dust has its own difficulty in the early universe. Heavy elements must first be made inside stars and spread by stellar winds and explosions. A very young galaxy can contain dust, but enough dust to strongly reshape its light requires a history of star formation and enrichment. The dust answer is possible. It carries a clock of its own. The third explanation is the buried black hole. Here the redness and compactness come partly from an accreting central object wrapped in dense gas. Broad spectral lines may come from fast motion near the black hole, or from scattering inside an ionized envelope. Weak X-rays may happen because high-energy radiation is absorbed or reprocessed before it escapes. This answer can connect several clues at once, which is why it has become important. But it also must explain why the black holes are there so early, how large they are, and why their light differs from more familiar active galactic nuclei. A hidden engine solves one problem by opening another. The dot becomes less like a galaxy with a black hole inside and more like a locked room, where the lamp, the smoke, and the walls shape the glow together. The fourth possibility is that some little red dots are temporary events rather than stable phases. A star passing too close to a black hole can be torn apart, producing a flare known as a tidal disruption event. In dense early clusters, repeated disruptions or related processes might create compact red accretion-like sources for limited periods. This kind of model is attractive because it explains why some objects could be brief, unusual, or connected to growing black holes without requiring every dot to be a long-lived galaxy type. But temporary events have to match the observed numbers, colors, spectra, and timing. A transient can explain a spark. A population requires a fire pattern. That is the challenge. These competing explanations are not enemies in a contest where one survives and all others vanish. The early universe may be producing a mixed family. Some little red dots may be mostly compact stellar systems. Some may be starbursts hidden by dust. Some may be active black holes wrapped in gas. Some may be transitional states where dense clusters, black hole seeds, star formation, and accretion overlap. From far away, different physical systems can collapse into similar colors and shapes. Webb sees their light, not their internal architecture directly. The danger is to confuse resemblance with identity. Two objects can both be red and compact for different reasons, just as two quiet rooms can hide different activities behind the same closed door. This is why astronomers need spectra multiple wavelengths and time. A spectrum can reveal broad lines, ionization signatures and redshift. Infrared data can test dust and stellar populations. X-rays can search for escaping high-energy accretion. Radio observations can look for jets or energetic outflows. Repeated observations can test whether an object changes like an active nucleus or flare. No single clue is enough for the entire class. The truth may emerge as a sorting process, not a single answer. The little red dots may divide into subgroups that only appeared unified when first images made them alike. The micro payoff is that the easy explanation fails because the dots are ambiguous in a physically meaningful way. Their ambiguity is not a weakness in the science. It is the science. It shows where early galaxies, dust gas, black holes, and dense stellar systems can produce overlapping signals. The black hole explanation remains powerful because it connects broad lines, compactness, and hidden energy. The stellar and dust explanations remain important because the early universe is full of rapidly forming galaxies whose light can mislead. Section 8 leaves the listener with a more careful picture. The little red dots are not a single answer waiting to be named. They are a sorting problem from the first billion years. And to see why the black hole interpretation cannot be dismissed, the next step is to look at one especially distant red dot, where the spectrum turns the hidden engine from speculation into a sharper possibility. Capers-LRD-Z9 matters because it gives the little red dot mystery a sharper edge. Until an object has a distance, a spectrum, and a physical interpretation tied to real features in the light, it can remain part of a cloud of possibilities. It may be ancient, but perhaps not as ancient as hoped. It may be red, but perhaps for several reasons. It may contain a black hole, but perhaps the evidence is only suggestive. CAPERS-LRD-Z9 narrows that uncertainty. Its redshift places it deep in the early universe when cosmic time is still measured in hundreds of millions of years rather than billions. Its spectrum shows broad hydrogen emission, a sign that gas is moving fast enough to make an accreting black hole difficult to ignore. The dot remains small in the image, but the spectrum gives it weight. One object cannot solve a population. It can change the seriousness of the question. The name itself sounds technical, almost cold, yet it marks something quietly dramatic. CAPERS refers to the survey that helped reveal it. LRD identifies it as one of the little red dots. The Z9 points to its high redshift, the sign that its light comes from a very early cosmic time. In ordinary language, this means that Webb is not seeing the object as it is now if it still exists in any recognizable form. Webb is seeing it as it was when the universe was young, before Earth existed, before the Sun existed, before most later galaxies had settled into the structures seen nearby. The light has traveled through almost all of cosmic history. By the time it reaches the telescope, the object has become both a point and a fossil. The broad line part of the discovery is crucial. Hydrogen gas can emit light at specific wavelengths like a signature written by atoms. If the gas is calm or moving slowly compared with extreme nuclear environments, the spectral line remains relatively narrow. But if the gas is racing under strong gravity, parts of the light are shifted in different directions and the line widens. In CAPERS-LRD-Z9, the broad line is interpreted as evidence for a broad-line active galactic nucleus, the kind of system where a black hole is feeding and gas near it is moving at great speed. The image alone would not be enough. The color alone would not be enough. The broadened light is the pressure point. It turns a red dot into a candidate for one of the earliest known actively growing black holes of this kind. That does not make the interpretation simple. The inferred black hole mass depends on assumptions about how the line was produced, how the gas is arranged, and how much surrounding material has reshaped the light. If dense gas around the source scatters and broadens the line, then the first mass estimate may not be the final one. If part of the ultraviolet light comes from the active nucleus, rather than the host galaxy's stars, then the stellar mass of the host may also be difficult to measure. This is why CAPERS-LRD-Z9 is powerful without being clean. It gives astronomers a clear case to study, but the case itself contains the same layered physics that makes the whole class mysterious. The clue is strong, the interpretation still has depth. Its timing is the deeper shock. At a redshift above 9, the object belongs to an era less than about 500 million years after the Big Bang. A black hole present at that stage must have followed a demanding path. It may have started from a massive seed, giving it a large beginning. Or it may have started smaller and gone through periods of especially rapid accretion. Either way, the object forces the growth problem out of abstraction. It is no longer only a question about theoretical seed channels or later quasars. It becomes a specific red point whose light carries the signs of fast gas around a central engine in a universe still under construction. The early universe is not a blank childhood scene. It already contains engines. A human-scale comparison helps, though it can only go so far. Imagine finding a large tree ring pattern in a forest that should still be saplings. The finding would not mean the forest has no rules. It would mean that some trees began differently, grew faster, or lived under conditions that allowed unusual development. CAPERS-LRD-Z. 9 is like that in cosmic form. It does not prove that every little red dot hides a growing black hole. It does not prove that all early black holes began as massive seeds. But it shows that at least one compact red object from a very early time carries the spectral behavior expected from active black hole growth. It makes the possible pathway visible. That visibility changes the surrounding debate. If one little red dot can host a broad-line active nucleus at such an early epoch, then similar objects deserve close attention. Their red colours and compact sizes are no longer merely curiosities of early galaxy light. They may be selection signs pointing toward hidden accretion. Some will turn out to be different. Some may be dominated by stars. Some may be dust-reddened galaxies. But the class cannot be dismissed as only a photometric oddity. CAPERS-LRD-Z 9 proves that a little red dot can be a doorway into early black hole growth. The micro-payoff is precise. The black hole interpretation is not just a dramatic possibility attached to small red sources. In at least this case, spectroscopy gives it a strong physical basis. That basis does not end the story, because the object also raises the next problem. If the black hole is truly growing inside a host that is still compact and early, then the balance between black hole mass and galaxy mass may be very different from familiar nearby systems. The dot may not only show a young engine, it may show an engine that looks too prominent for the small galaxy around it, and that is where the next layer begins. The overmassive illusion begins when a tiny red point is asked to carry too much meaning at once. In the first readings of some early compact sources, the light could be fitted as if it came mainly from stars. If that were true, the host galaxies might contain surprisingly large stellar masses for their age, packed into regions so small and so early that the young universe would seem to have built them with uncomfortable speed. The problem was not merely that the objects were bright. Brightness can come from many things. The problem was that brightness, color, compactness, and distance together could make a galaxy look older, heavier, or more mature than the cosmic clock easily allowed. A red dot became a scale. A faint object became a question about mass. But mass in astronomy is often an inference, not a label written on the sky. The light must be translated, and translation can mislead. To estimate the stellar mass of a distant galaxy, astronomers ask what kind of stars could produce the observed light. Young hot stars shine strongly in ultraviolet. Older stars can add redder light. Dust can remove some wavelengths and leave others. Gas can glow in emission lines. An active black hole can add its own continuum and line radiation. At great distance, when the object is compact and unresolved, these ingredients can blend. If one model assumes that most of the light belongs to stars, the inferred galaxy may become heavy. If another model allows a buried active nucleus to contribute, the host may become lighter. The same photons can lead to different masses, because the photons do not come with labels saying which engine produced them. The measurement is real. The interpretation is the fragile part. This is why the little red dots can seem to threaten galaxy formation, and then become less threatening without becoming less interesting. If their red light is interpreted as the glow of many stars, then some appear like dense galaxies that form too much too quickly. If a significant part of their light comes from accretion, dense ionized gas, or reprocessed radiation near a black hole, then the stellar mass of the host can be lower. The galaxy no longer has to be impossibly heavy. The black hole may also no longer have to be as massive as early broadline estimates suggested if scattering inside dense gas widens the lines and changes how the motion is read. The object remains strange, but the kind of strangeness changes. It moves from impossible maturity toward hidden youth. A useful image is a city seen at night through fog. From far away, one bright glow might be mistaken for a huge district filled with lamps. But if much of that glow comes from one central searchlight diffused by mist, the city around it may be smaller than it first seemed. The brightness is not false. The distance is not false. The glow is real. What changes is the source assigned to the glow. Little red dots may work in a similar way. Their light arrives honestly after crossing most of cosmic history. But the balance between stars, gas, dust, and a central engine is not written plainly into the image. Webb gives astronomers the signal. Models must decide how to divide it. This is also where the relationship between black holes and host galaxies becomes uncertain. In the nearby universe, supermassive black holes often correlate with properties of their host galaxies, especially the central bulge. The relationship is not a simple law for every object, but it gives a familiar expectation. Black holes and galaxies grow together in a connected way. If little red dots contain black holes that appear too large compared with their small hosts, they may seem to violate that nearby relationship. But the early universe does not have to look like the nearby universe. A compact young system may pass through a stage where the black hole grows quickly while the host is still assembling, or the host mass may be underestimated or overestimated depending on how the light is modelled. Or the black hole mass may be biased by line broadening that is not purely orbital. The ratio itself becomes part of the puzzle. The overmassive impression may therefore be partly real and partly observational. Some early black holes may genuinely be ahead of their galaxies, growing rapidly before the surrounding stellar system catches up. Others may only appear ahead because dense gas changes the spectrum and active light contaminates the stellar estimate. Both possibilities matter. If black holes can lead galaxy growth for a time, then feedback radiation and gas heating may influence the host earlier than older pictures assumed. If the overmassive signal is mostly an illusion, then the little red dots still teach a different lesson. Early compact objects are difficult to weigh because their light is blended with hidden engines and dense material. Either way, the dots expose a measurement problem at the edge of cosmic time. They show how a small uncertainty in interpretation can become a large uncertainty in history. This does not make the science weaker, it makes it more honest. A universe seen from more than 13 billion years away cannot be weighed like an object placed on a table. Every estimate passes through models of stars' gas-dust geometry, accretion, and cosmic expansion. Webb has improved the evidence, but better evidence can reveal deeper ambiguity. The little red dots may not break cosmology. They may reveal that the first reading of their light was incomplete. Their apparent overmassiveness may be a warning that early galaxies cannot be treated as simple stellar lanterns, when black holes and dense gas may be shining inside them. The micro payoff is, the dots are not necessarily too massive to exist. They may be too complex to weigh with one simple assumption. And once the illusion is recognized, the next mystery becomes more fundamental. If some of the red light comes from young black holes, where did those black holes begin? And what kind of seeds could grow inside the dark nurseries of the first galaxies? A seed black hole is a small beginning with an enormous future placed on its back. The phrase sounds simple, as if the early universe only needed to plant a dark point and wait. But the seed is where the little red dot mystery becomes older than the dots themselves. If some of these compact red objects contain young accreting black holes, then the visible glow is not the first chapter. Somewhere before the glow, before the cocoon, before the broad spectral line, a black hole had to begin. It may have begun as the corpse of a massive star. It may have begun as the direct collapse of a heavy gas cloud. It may have begun through collisions and runaway growth in a dense cluster. Each path changes the clock. Each path changes what the early universe was capable of doing in the dark. The seed is small only at the start. The light seed pathway is the most familiar because it begins with stars. The first generations of massive stars could live fast and die violently, leaving black holes behind. These remnants might weigh tens or perhaps hundreds of solar masses depending on the star and the collapse. From a human perspective, that is already enormous. But next to a supermassive black hole, it is only a beginning. To grow from a stellar remnant into a black hole, millions of times the sun's mass, the seed must feed again and again. It must avoid long starvation. It must remain where gas can reach the center. It must grow while the young galaxy around it is changing, heating, forming stars and sometimes being disrupted. The path is possible, but it asks a great deal from time. The heavy seed pathway begins with a more dramatic collapse. In some early environments, a large gas cloud might avoid breaking apart into many ordinary stars and instead collapse more directly toward a massive black hole. This gives the future engine a head start. A seed born thousands, tens of thousands, or more solar masses heavy does not need as many growth steps to become impressive within the first billion years. But heavy seeds require special conditions. Gas must cool in the right way, or not cool too efficiently. Radiation from nearby sources may need to suppress certain molecules that would otherwise help the cloud fragment. The dark matter halo must gather material while chemistry and turbulence must not turn that material into a normal star cluster too quickly. A heavy seed solves the time problem by making the birth problem harder. There is also a cluster route where dense groups of stars and stellar remnants crowd together until collisions, mergers, and runaway processes build a larger black hole. This pathway does not require one cloud to collapse cleanly into a single heavy object. Instead, it relies on crowding. In a young compact galaxy, the center may be dense enough for massive stars to sink inward, collide, and leave remnants that merge. The result could be an intermediate beginning heavier than a normal stellar remnant, but perhaps less demanding than direct collapse. The difficulty is again not imagination but numbers. How often would such clusters form? How efficiently would their remnants merge? Could they retain black holes after energetic kicks from mergers or explosions? The early universe offers dense places, but density alone is not a guarantee. Little red dots matter because they may be close to the moment when these pathways become observable. They're not the seeds themselves if the black hole has already begun accreting. They may be the nursery light around seeds that have entered their first serious feeding phase. A buried black hole inside dense gas is like a young tree whose roots are hidden under soil. The visible sign is not the seed, but the early growth breaking the surface. Webb cannot watch the birth directly. It sees the heated gas, the reddened glow, the broadened lines, and the compact source after the process has already begun. Yet that is still precious. It is much closer to the beginning than the bright quasars found later, whose black holes are already enormous. This is why the seed question cannot be separated from the cocoon question. A dense envelope might hide the black hole, but it might also reveal the kind of environment needed for growth. If early black holes grow fastest when embedded in gas-rich compact systems, then the little red dots may be signposts of fuel-rich nurseries. If heavy seeds are common, the dots may be the first visible stage after direct collapse. If light seeds can grow rapidly through episodes of super Eddington accretion, the dots may show the hidden conditions that make such growth possible. The same red point can become evidence for different origins depending on how its mass luminosity line widths and host galaxy are interpreted. The object is visible. The beginning remains inferred. The micro payoff is that the little red dots do not merely ask whether young black holes exist. They ask what kind of beginning the universe allowed. A light seed tells one story in which ordinary stellar death begins the ladder and extreme feeding climbs it. A heavy seed tells another in which rare gas clouds collapse into engines already large enough to matter. A cluster pathway tells a third in which crowding and mergers build the bridge between stars and supermassive darkness. None of these answers has to explain every object. The early universe may have used more than one channel. That is part of the difficulty and part of the beauty. The seed problem remains unresolved because the evidence is indirect. Webb can measure light redshift spectra and signs of rapid motion, but it cannot rewind the object to the moment the black hole first formed. Models must connect the present clue to the past beginning. Future observations may narrow the choices, but the current lesson is already clear. If little red dots contain accreting black holes, then the hidden childhood of supermassive black holes is not only a theoretical gap, it may be glowing faintly in Webb's fields wrapped in red light. Yet to decide which seeds are real, astronomers need another kind of evidence, not only the light Webb detects, but also the light that seems to be missing. The missing X-rays make the little red dot mystery feel less like a clean discovery, and more like a locked room with the light turned low. If an object contains a feeding black hole, astronomers often expect X-rays to be part of the evidence. The inner accretion flow around a black hole can become extremely hot. Close to the center, matter loses gravitational energy heat surrounding plasma and can produce high-energy radiation before it disappears from view. In many active galactic nuclei, X-rays are one of the clearest signs that a compact engine is present. They do not show the black hole itself, but they show the violence of matter near it. That expectation is why the little red dots became so puzzling. Some of them show optical or infrared spectral hints that look consistent with accretion, yet the X-ray voice is often faint, absent, or difficult to detect. The silence matters. It is tempting to treat missing X-rays as evidence against black holes. In a simple version of the story, a feeding black hole should glow in high-energy light, and if that light is not found, the black hole answer weakens. But the real situation is less direct. X-rays can be produced and still fail to escape clearly. Dense gas can absorb them. A thick accretion flow can trap some radiation. Material surrounding the nucleus can scatter and reprocess high-energy photons into longer wavelengths. Distance also matters. These sources are extremely far away, and even strong emission can become difficult to detect after crossing most of cosmic history. Observatories that search for X-rays are powerful, but they are not magic. A non-detection is not the same as absence. It is a measurement shaped by sensitivity, distance, absorption, and the true nature of the source. Still, a missing signal is not empty. It becomes a clue with two meanings. On one side, weak X-rays can support the idea that the black hole, if present, is buried. A dense cocoon can hide the high-energy radiation, while allowing reprocessed infrared and optical light to escape. In this reading, the little red dots are not failed active nuclei. They are young active nuclei seen through heavy wrapping. On the other side, weak X-rays can support competing explanations. If no strong high-energy engine is needed, perhaps some dots are compact star-forming galaxies, dusty stellar systems, or other sources whose light does not require a black hole at all. The same absence can be used by both sides. That is what makes it scientifically useful and scientifically difficult. A useful comparison is a storm behind a mountain range. A person in a valley may not hear thunder clearly, not because the storm is absent, but because rock distance and wind have changed the sound. Yet silence in the valley could also mean there is no storm nearby. To decide between those possibilities, the listener would need other clues: flashes of light above the ridge, changes in air pressure rain moving across the ground. Little red dots require the same kind of layered reasoning. X-rays are one channel, spectral lines are another, infrared color compact size variability radio emission, and host galaxy estimates all add pieces. No single silence can carry the whole verdict. The problem becomes even more interesting because at least one object with little red dot-like properties has been connected to X-ray emission. That discovery does not mean all little red dots are X-ray sources. It does not erase the earlier weakness. Instead, it offers a possible bridge. If one compact red source can glow in X-rays while resembling the broader population, then some buried engines may occasionally reveal themselves, perhaps through thinner gas, a stronger accretion state, or a moment when high-energy photons find a path outward. The X-ray dot becomes a rare opening in the veil. It suggests that the missing light may not be missing in every case. It may be hidden, variable faint, or only visible under the right conditions. This is why future X-ray observations are so important. Infrared telescopes can find the red sources and read their spectra. X-ray observatories can test whether hidden engines are leaking high-energy radiation. Deep exposures can search for individual detections. Stacking many faint sources together can reveal whether the population on average produces more X-rays than background noise. Better models can compare little red dots with local active nuclei narrow-line Seyfert galaxies and rapidly accreting black holes, not because the nearby universe is identical, but because known systems give physics a set of reference points. The early universe is unfamiliar, but it is not lawless. It must still speak through radiation, motion absorption, and energy balance. The micro payoff is that weak X-rays do not close the black hole case. They define the kind of black hole case that can survive, a clean exposed. Mature active nucleus is harder to reconcile with many little red dots. A young embedded gas-wrapped accretor remains plausible. So does a mixed population in which some red dots contain black holes and others are dominated by stars or dust. The absence of X-rays therefore narrows the possibilities without choosing only one. It tells astronomers that if black holes are present, their environments matter as much as the engines themselves. The hidden material is not a minor correction. It is part of the identity of the object. Section 12 leaves the mystery in a sharper place. Webb has opened the infrared door. Spectra have hinted at fast gas. Dense cocoon models can explain why ordinary active galaxy expectations may fail. But X-rays ask for independent confirmation from a different kind of light. If more little red dots are detected in X-rays, the buried black hole picture grows stronger. If deep searches continue to find almost nothing, stellar and dust-based explanations gain weight, or the cocoon must become even more effective at hiding the engine. The next step is not louder speculation. It is sharper testing using every wavelength that can reach across ancient time. The next stage of the little red dot mystery belongs to tests that can pull one blended signal apart. Webb has already shown why the objects matter: compact red sources, early cosmic timing, strange spectra, and possible signs of hidden accretion. But Webb alone cannot make every ambiguity disappear. A red colour can belong to distant dust gas, old-looking stars, or reprocessed light from a buried engine. A broad line can point toward fast gas near a black hole, or toward scattering inside dense, ionized material. Weak X-rays can mean no black hole, or a hidden black hole, or a black hole too faint for current observations at that distance. The same clue can lean in more than one direction. That is why the future of the field is not one grand image. It is a sequence of sharper separations. The first separation comes from deeper spectroscopy. A spectrum is a slow unweaving of light. Instead of treating the dot as one color and one brightness, spectroscopy asks which atoms are glowing, how broad their lines are, where those lines fall after cosmic redshift, and whether different features tell the same story. Hydrogen lines can reveal gas motion. Oxygen lines can help trace ionization and star-forming conditions. The shape of the continuum can test whether stars or an active nucleus dominate the glow. If many little red dots show broad lines, high ionization features and patterns consistent with accretion, the black hole interpretation strengthens. If many show signatures better matched to compact stellar populations, the story bends back toward early galaxy growth. The answer will not come from a label, it will come from a pattern. The second separation comes from wavelength. Infrared light is powerful because ancient starlight and accretion light have been stretched into Webb's range, but other wavelengths ask different questions. Mid-infrared observations can test hot dust and reprocessed radiation. Submillimeter and millimeter observations can search for cold dust and gas reservoirs. Radio observations can look for jets, compact cores, or the absence of them. X-ray observations can search for the high energy leakage expected from accretion, especially if holes open in the surrounding gas. Each wavelength is like a different door into the same locked building. One door may show the heating system, another may show the walls, another may show whether a hidden engine is shaking the frame. The object stays small, but the physics becomes less hidden. The third separation comes from time. A galaxy dominated by steady starlight should not flicker in the same way as a compact accreting source. A black hole feeding through uneven gas can vary as material falls, inward heats, dims and brightens. A tidal disruption event or temporary flare can fade in a distinct way. Repeated observations can therefore test whether little red dots are stable early galaxies' active nuclei, or transient phenomena. Time is difficult at such distances because the objects are faint, and because cosmic expansion stretches observed timescales. But even slow changes can matter. A source that brightens or fades in a way linked to accretion becomes harder to explain as a passive stellar system. A source that remains steady and lacks other active signs may move toward a different category. The dot becomes a watch. The fourth separation comes from the population itself. One object can be exotic. 100 objects can reveal an evolutionary stage. Astronomers need samples selected in consistent ways, with redshift spectra, luminosity sizes, and follow-up measurements that can be compared rather than admired separately. If little red dots cluster in a narrow cosmic time window that supports the idea of a temporary phase, if their properties divide into clear subgroups, the class may be a visual mixture rather than a single physical kind. If black hole-like signatures appear most often in the reddest, most compact or most luminous objects, the selection rules become meaningful. If not, the apparent family may dissolve into several unrelated early universe systems. A catalogue can become a map of hidden categories. Better models are just as important as better observations. The light from a little red dot must pass through assumptions before it becomes a mass, a star formation rate, a black hole estimate, or a growth history. Models must include stars, dust, nebula gas, accretion disks, scattering envelopes, absorption geometry, and cosmic redshift. If a model leaves out the active nucleus, it may overestimate the stellar mass. If it leaves out dense gas, it may overestimate the black hole mass from a broadened line. If it assumes nearby active galaxies are perfect templates, it may miss the strange conditions of the first billion years. The model is not the truth, it is the translator, and the translator must learn the language of early compact systems. The micro payoff is that the little red dot mystery is not waiting for one magical observation. It is waiting for agreement among many kinds of evidence. Webb can identify and dissect the infrared source. X-ray telescopes can test for hidden high-energy leakage. Radio and millimeter observatories can search for gas dust and energetic outflows. Repeated observations can test variability. Statistical samples can test whether the objects are a phase, a mixture, or a rare pathway. The stronger answer will come when these clues stop pulling in separate directions. Until then, the careful conclusion is that the little red dots are testable, not mystical. Their mystery is not protected by ignorance. It is exposed to measurement. This is where the story becomes larger than classification. If future tests show that many little red dots contain buried accreting black holes, then Webb has found a formative stage in the growth of supermassive black holes. If many turn out to be compact stellar systems, then the early universe built dense galaxies with surprising speed. If the population is mixed, then the dots become a sorting key for several hidden processes acting at once. Each outcome changes the early universe story in a different way, and that is why the next section must step beyond instruments and ask what the red dots would mean if they truly mark the moment when galaxies and their central black holes began growing together. The phrase "black holes before galaxies" is powerful because it sounds like a reversal of cosmic order. It suggests darkness, arriving first engines forming before the homes that should contain them, gravity writing the center of the story before starlight has built the scene around it. But the careful meaning is subtler, and the subtler meaning is often more interesting. Little red dots do not prove that black holes existed before all galaxies. They do not prove that the early universe skipped the usual steps of structure formation. They point instead to a possible overlap, a stage where the central black hole and the young host system are growing so close together inside the same gas supply that separating one from the other becomes difficult. The old question asks which came first. The red dots suggest that in some places the answer may be neither in a clean way. Galaxies are not built like containers waiting for a black hole to be placed inside. They are gravitational systems in motion. Dark matter gathers gas, gas cools and falls, inward stars form explosions, enrich the material, and gravity keeps reshaping the whole arrangement. A black hole inside such a system is not an ornament added later. It can feed from the same gas that makes stars. It can heat that gas. It can help drive outflows. It can alter how future material falls inward. In mature galaxies, this relationship has had billions of years to become recognizable. In the first billion years, the same relationship may be raw, compressed, and hidden. The host may still be small, the gas may still be dense, the black hole may still be buried. Everything is happening close together. This is where the little red dots become more than a classification problem. They become a challenge to a simple mental picture of cosmic growth. The mind like separate chapters, first dark matter halos, then gas, then stars, then galaxies, then central black holes. The real universe may not respect those divisions so neatly. The first stars can leave black hole remnants while early galaxies are still assembling. Dense clouds can collapse while stellar nurseries are forming nearby. Gas can feed stars and black holes at the same time. Radiation from one process can change the conditions for the other. A young galaxy is not a finished stage on which a black hole later appears. It may be the very environment where the black hole learns to grow. The measurement is small. The implication touches the order of the chapters. To feel the scale, imagine watching a city from so far away that every neighborhood, street, furnace, and window blends into a single reddish glow. If one central source inside that city is unusually bright but wrapped in fog, the glow may not tell where the city ends and the source begins. The observer can detect warmth, color, and perhaps motion in the air, but not the clean boundaries of the system. Little red dots are cosmic versions of that blurred view. They may contain stars and gas and dust and an accreting black hole inside one compact unresolved signal. Their redness does not belong to one process alone. Their light may be the combined voice of a young system still too entangled to separate by sight. That is why the question before galaxies must be handled gently. It is not a slogan. It is attention. If black holes in little red dots are confirmed across a large fraction of the population, then early black hole growth may have been more common than older surveys revealed. That would not erase galaxy formation. It would make galaxy formation more mutual. The galaxy would not simply grow first, and later feed a central monster. The central engine might grow while the galaxy is still gathering itself, changing the gas supply and perhaps shaping the next generation of stars. In that picture, black holes are not late consequences alone, they are participants. They enter the story before the host has become familiar. They may help define what the host becomes, but even this must remain cautious. Some little red dots may not contain active black holes. Some may be compact stellar systems. Some may be dusty starbursts. Some may be transient events. The philosophical turn is not that the universe has revealed a single dramatic secret. It is that the boundary between categories becomes less rigid when we look far enough back. Galaxy and black hole host and engine star formation, and accretion, light and hiding material in the early universe, these may be blended phases of one assembling structure. The objects are not simple because the era is not simple. The first billion years is not a calm preface. It is a construction zone filled with gravity, radiation, collapse and transformation. The micro payoff is that little red dots make the question more mature. Instead of asking whether black holes came before galaxies in an absolute sense, the better question is whether black hole growth became important before galaxies looked mature. That version is scientifically safer and more revealing. It allows early galaxies to exist. It allows black holes to form inside them, but it also allows the black holes to grow quickly enough and hide deeply enough that they become central actors while the host is still young. The red dots may show not a reversal, but an entanglement. They may reveal that the first galactic centers were not quiet places waiting for time to pass. They were crowded, luminous, obscured, and already changing. This is why the final view must return to the image itself. A little red dot is not impressive because it is large on the sky. It is impressive because it compresses a difficult relationship into a nearly point-like source. It asks how stars, gas dust, and black holes shared the same early environments. It asks how much of a galaxy's future may be shaped while it still looks like a small red mark in Webb's field. And it prepares the final synthesis where the opening mystery can be seen again with less certainty, but more understanding, not as proof that black holes came first everywhere, but as evidence that the early universe may have built galaxies around hidden engines sooner than expected. The little red dots return at the end to their first strange simplicity. They're still only small red marks in Webb's fields, still unresolved in many images, still far enough away that their light has crossed almost the entire age of the universe. Nothing in their appearance alone forces the eye to stop. A dot is the least dramatic shape the sky can offer. Yet the journey through their evidence changes what that dot means. It is no longer just a faint early galaxy candidate. It is no longer just a colour. It has become a compressed record of distant gas dust stars, accretion, hiding and growth. The first image was quiet. The finished question is not. What looked like a point now becomes a doorway into the first crowded centres of galaxies where young black holes may have been feeding before their surroundings looked mature. The deepest lesson is not that every little red dot is a black hole. That would be too simple, and it would be more certain than the evidence allows. Some little red dots may be compact stellar systems built from dense early star formation. Some may be galaxies reddened by dust or shaped by unusual stellar populations. Some may be transient events or mixed systems where several processes overlap. But some, perhaps many, carry signs that make accreting black holes difficult to ignore: broad spectral lines, compact brightness, early timing, and strange weakness in the high-energy signals that mature active nuclei often display. The category remains unsettled. That is part of its importance. It shows the early universe not as a neat museum of finished types, but as a place where categories are still being made. Webb's gift is not only discovery, it is discomfort. It forces the familiar story to bend without breaking. Galaxies still form through gravity, gas stars, mergers, cooling, and time. Black holes still grow by accreting matter, and sometimes merging with other black holes. These rules remain, but the little red dots suggest that the order of the story may be less tidy than older pictures made easy to imagine. The central engine may not always wait until the host galaxy is large, calm, and recognizable. It may grow while the host is still compact red and wrapped in dense material. It may influence the gas supply before the galaxy is settled. It may hide inside the same cloud that feeds stars. The house and the furnace may be rising together. That is the shift. This shift also changes the meaning of early cosmic time. Hundreds of millions of years after the Big Bang can sound vast, but for building supermassive black holes, it is a short and demanding interval. Seeds must form, gas must fall, radiation must escape or be trapped, stars must enrich the surroundings, dense structures must survive feedback and motion. If little red dots contain young accreting black holes, then they may show that the universe found efficient ways to make central engines while galaxy assembly was still unfinished. Perhaps some seeds were heavy. Perhaps some feeding was unusually rapid. Perhaps dense cocoons both fed and hid the black holes. Perhaps several channels operated at once. The dots do not choose one answer. They place the question where it can be measured. The human scale image is a lantern seen through a red veil at the edge of dawn. The viewer cannot see the lamp directly. The veil glows, the air moves, and the source becomes visible only through what surrounds it. A little red dot may be like that. Not the black hole itself, not the galaxy alone, but the glow of an early system whose parts are still entangled. Stars shine. Gas scatters, dust absorbs. A hidden engine may heat the center. Ancient expansion stretches the light before it reaches Webb. By the time the signal arrives, it has become a tiny mark carrying several histories at once. The dot is small because distance has compressed it. The story inside it is large because time has preserved it. The final answer then is careful. Are the little red dots signs of young black holes growing earlier than expected? Some of them appear to be strong candidates, and some evidence points toward buried accretion in compact early systems. But the class is not yet a single solved object. It is a testing ground. Each new spectrum, each deeper X-ray search, each mid-infrared measurement, each sign of variability, each improved model can sort the family more finely. Some dots may move into the black hole column, some may move into the stellar column, some may remain mixed because the early universe itself was mixed. The power of the discovery is not that it ends the debate. The power is that it gives the debate objects to hold. When the opening image returns, it no longer looks empty. The red points are not just specks behind brighter galaxies. They are possible records of a time when black holes, stars, and gas were still learning their roles inside the first dense systems. They may show that the centers of galaxies were active earlier than expected, not as finished giants, but as hidden engines in formation. They may explain how later quasars found their beginnings. They may reveal that what seemed like a small red point was a young cosmic center wrapped in its own fuel. The mystery remains quiet, but it is deeper now. Webb has not shown a universe where black holes simply came before galaxies. It has shown a universe where the boundary between a growing galaxy and a growing black hole can blur in the first billion years, where a dot can be a phase where missing light can be evidence, and where the smallest marks can carry the earliest engines. The little red dots stay little on the screen, but in the story of cosmic origins they have become enormous. The little red dots leave behind a quiet change in perspective. They do not turn the early universe into a place of certainty. They make it more carefully mysterious. What once seemed like a distant population of compact red objects now becomes a set of questions about how darkness grows, how galaxies assemble, and how much of cosmic history can be hidden inside light that barely covers a pixel. A point can be a galaxy. A point can be gas. A point can be dust, stars, motion, and perhaps a black hole feeding behind its own veil. Webb has made the point readable but not simple. That is the lasting beauty of the mystery. The little red dots do not need to shout. Their power comes from restraint. They sit at the edge of observable time, carrying light from an era when the universe is still young enough for the first great structures to be uncertain, crowded, and unfinished. If some of them contain growing black holes, then the first galactic centers were not silent places waiting for maturity. They were already active, already gathering fuel, already shaping their surroundings from within. And if some of them are not black holes, that does not weaken the story. It widens it. It means the early universe was rich enough to produce several kinds of compact red systems, each hiding a different path toward galaxies, stars, dust, and central engines. The answer may not be one door, it may be a corridor, so the dots remain in the dark field small and red and patient. They are not proof of a single beginning. They are evidence that the beginning was layered. In their faint light, the young universe does not look empty. It looks unfinished, alive with hidden growth and still quietly giving up its first secrets.